Hello, today we'll shortly talk about solutions to the equation 4a plus 6b equal to k. And we consider a, b, and k to be non-negative integers, and k we just restrict to the case where k is even, because, there are no solutions in a and b for this equation if k is odd. Okay, let's start with the first observation. So let's take k equal to 0. Then we get the equation 0, 0, so a and b 0. K equals to 2, we get no solution. For 4, we get 1, 0. And for 6, we get 0, 1. And of course, up to now, we don't get any more solutions, just the ones I've written down. Here we get 0. Oops, not 0. 1, 1. And for 12 is the first time where we get two solutions, namely 3, 0, and 0, 2. And we can go on. So here we get now one solution, and this one is, let's check, 14, so that's a 2 and a 1. And first let me tell you a little more. So we'll also shortly talk about how this is related to modular forms, but not very deeply, I just mention it. And now we want to solve this for general k. So we want to get the number of solutions. And we'll do this via generating functions. So let me show you how we can solve this. So we define a sequence an, or maybe better call it ak, to be the number of a, b, such that 4a plus 6b is equal to k. Okay, and that's a sequence. So far so good, and we want to get a recurrence relation, and therefore we use generating functions. So we want to consider ak, and now we just write it as a formal power series. And what we note, so we write them as, so the AKs are given by this equation here. And what you can now easily check just by the summation formula. So we can write this as 0 to infinity x to the 4l times a sum, let's say, from m, then x to the 6m. And so this now, so you can easily check that the product of these two gives us the series with coefficients ak. And now we just use geometric series. So we get 1 over 1 minus x to the 4th times 1 over 1 minus x to the 6th. And now, so it's not entirely clear why we do this, but we want a recursion of length 12, so that's the hint. It's probably not entirely clear why we want a recursion of length 12. But if we assume that, we can just look at this thing here. So we look at 1 minus x to the 12, and then the series we started with, and well, that's now just 1 minus x to the 12 divided by 1 minus x to the 4 and 1 minus x to the power of 6. Now we can rewrite this. You can check that this is 1 minus q squared, 1 minus x squared plus x to the 4 divided by 1 minus x squared. And well, now we use again the geometric series, so we get 1 minus x squared plus x to the power of 4, and then sum from 0 to infinity x to the 2k. And well, what's this? This gives us a sum from 0 to infinity x to the 2k, then minus a similar sum, so where we have x to the 2k plus 2 plus another sum like this where we get x to the 2k plus 4. Okay, so that's what we have. And now let's see, what does this give us? So let's say we take k at least 12, then we get that so here we have, so we first look at this here. So we look at the coefficient of x to the k, so we get that x, so a k, and then minus a k minus 12, and this is the same as the coefficient on the right hand side. But on the right hand side, the coefficient for k at least 12 is just a 1, because it's 1 minus 1 plus 1, so that's a 1, and so we get that ak is equal to ak minus 12 plus 1. And well, now we know what the sequence looks like, because we have calculated the first 12, or even up to 10 is enough. And then we know that we have, let's take for instance 22. We know there have to be 2 solutions. Let's look for them. Well, now I have to think a little bit. So we have 18 and 4, so 1, 3. And we also have, let's think, so if we have 4 fours and 1 sixth, 1 sixth, then we have 16 plus 6, which is also 22. And yeah, so we have 2 solutions here. Okay, so far about the number of solutions. And now if you know a little bit about modular forms, you might know that the space of modular forms of SL2C, so just consider the full modular group. And then we can consider this graded algebra over of modular forms. So mk are the modular forms of weight k, and this is isomorphic to the polynomial ring in two variables over the complex numbers. And the reason, so one can use these sequences here in that we can calculate, so the dimension of, one can show that the dimension of mk is given by the same numbers as these ak's, and then one can show that Eisenstein series E4 and E6 generate this algebra, so they generate it as an algebra, not as a module, but as an algebra, and then you map E4 to X and E6 to Y, and then if you know, so you can show surjectivity. So, and when you know that, then you get you can show injectivity using the dimension and that the number of solutions to this equation here are the same as the dimension of these mk spaces. Okay, but that's just a rough sketch. And what I mainly wanted to discuss were the generating series. Okay, thanks for watching. Have a good day.